Hello everyone, I'm Sindhu Hegde and I'll be presenting our work on gesture synchronization. Let us begin with a simple question. From the video clips shown in the slides, can you identify who is speaking in these videos? Here's the first example.
It's the beginning of December. So yeah, very clever machine.
Here's another example.
Huge ass. He's like the poor man's version of Ryan Reynolds.
Okay, so we saw these videos and the answer to the question is yes. For us as humans, this is a pretty straightforward task to identify the target speaker from these videos. Now, in computer vision literature, this is known as active speaker detection. And traditionally, the current works rely on signals from lip movements to identify the active speaker. However, if we carefully observe these videos, none of them have clearly visible lip movements. But all of them have one other signal in common, which probably we all used to guess the speakers in these videos, and that is body movements or gestures. And that is exactly the focus of our work, where the objective is to analyze if there is any natural correlation that exists between speech and gestures and use these signals to predict the active speaker. We propose a new task in this work known as gesture synchronization to determine if a person's gestures are correlated with their speech or not. We all know about the lip synchronization task, but here in this work, we are introducing gesture synchronization with an aim to identify to what extent it is possible to answer the question who is speaking from gestures alone without the need of a talking head to be available. We will now review some of the existing lip synchronization works and understand the challenges of using them in certain real-world applications. The lip sync problem has been well explored in literature and solved in prior works. It is a strong signal because speech and lip motion are dense in time and are causally related. We will see some of the examples below.
Sorry it didn't fly. Sorry it didn't fly.
Rocket and Matt wanted to know if anyone had 5 litres of bleach. Rocket and Matt wanted to know if anyone had 5 litres of bleach.
The heat maps shown on the right highlights the sound source, so basically the lip movements of the active speaker. And this way, lip sync cues are used to determine who is speaking. But then, the question arises as to what happens if the face or lips are not visible. And there could be various such scenarios. For example, detecting if a person is speaking from a long distance where the lips are too small, or scenes in movies where there are lots of pose, camera angle, and scene changes. One such example where the lips are occluded is shown below. So in all these cases, relying on traditional lip synchronization signals will not be applicable. Thus, our proposal is to determine who is speaking from gestures alone. This is a very challenging problem because the correlation between speech and gestures is much looser than that between speech and lip motion. Now that we know the importance of using gestures, let us proceed to explore our architecture. So this is a brief overview of our method. We have 2 streams of input. One is the visual stream and the other is the audio stream. For the visual stream, we experiment with raw RGB frames as well as keypoint representations. The visual encoder ingests one of these representations and generates visual features. These visual features act as input to the transformer encoder, and then we use an MLP to get the final visual embeddings. In the audio stream, we represent the speech using Mel spectrograms, which are ingested by the speech encoder. These speech features generated by the encoder are further projected using an MLP to obtain the final speech embeddings. We now have 2 sets of vectors with us from two input streams. One is the visual embeddings and the other is the speech embeddings. If the audio and the video are in sync, then the scalar product between these embeddings should be very high. And on the other hand, if they are out of sync, then the scalar product should be low. This forms the core of our network, the synchronization training using contrastive laws. So this was the brief overview of our network. Before we look into the details of the major modules involved in our architecture, let us understand the task and the way we use the data more clearly. To enforce the model to learn the synchronization between gestures and speech, we set up a self-supervised contrastive learning framework. We create synthetic data as shown in the example below. Consider a sequence of frames and their corresponding audio signal. a subset of these frames, and the corresponding audio is randomly selected. And this forms the positive pair because the audio and the video are in sync. Now, to get the negative pairs, we consider the same subset of frames and shift the audio signal. This forms the negative pair since the audio and the video are no longer in sync, they are completely out of sync. Such negative pairs are created using a simple shift operation. We now move on to the major modules involved in our architecture, starting with the video representations. The first one is the raw RGB frames. An important aspect here to note is that of the face masking. Since we do not want to consider any information about faces and rely entirely on gestures, we mask the face region in the input frames. The next representation is keypoints, where we have two different types. The first one is the keypoint image representation, where we extract the keypoints and render the XY coordinates onto an image. A sample of this representation is shown here. And the next one is the keypoint vector representation, where we directly use the normalized keypoints as inputs. So now, one of the questions that arise at this stage is, why do we even need keypoint representations? Well, there are multiple reasons to do so. First, the keypoint vector representation is very efficient. It is 5.5 times faster than RGB. Second, it is very easy to switch between different parts and consider the regions of input, whereas for RGB, we need a separate masking. And third, using keypoints directly discards unnecessary information like background or different lighting conditions and so on. Moving on, let us now look at how a model is trained to capture the correlation between speech and gestures. Once we have extracted the visual embeddings and the speech embeddings, we train our network in a self-supervised contrastive manner using cosine similarity. The training objective here is to maximize the similarity between the synchronized video and speech, that is the positive pair, and minimize the similarity for all the negative pairs, that is essentially between the shifted versions of the audio input, because these shifted versions are completely out of sync. So this was the brief about our method and architecture. To train and evaluate the performance of our network, we use LRS3 dataset, which is a large-scale dataset of more than 400 hours of video data sourced from TED Talks. We consider two tasks for evaluation. The first one is the synchronization task, for which we have trained the model, and the second task is an application to determine who is speaking from a crowd. Note that we do not train or fine-tune our model for this task, but rather just use the synchronization scores to predict the active speaker. We will start by looking into the results for the synchronization task. The aim here is to predict by how many frames the video is out of sync with the audio. The output frame offset prediction from the model is used to sync correct the input video. We will visualize the input video on the left and show the resultant sync corrected video on the right.
Honestly revolutionized my life. Over the next 22 years, my colleagues and I would build the world's, and quite honestly revolutionized my life. Over the next 22 years, my colleagues and I would build the world's.
So the input on the left is clearly out of sync. Also, note that the faces are shown here only for reference but are never used in our network. Now, our model accurately predicts the number of frames the video is off sync with the audio and is able to sync correct the video as shown on the right. Let us see another example.
Altro non sono che noi stessi. La fantasia. Altro non sono che noi stessi. La fantasia.
It is interesting to note here that our model works for any language, although we have only trained the model for English videos. Coming to the quantitative results, the plot here shows the synchronization accuracy on LRS3 dataset averaged over different number of frames, specifically 50, 75 and 100 frames. We can observe that RGB representation achieved the best performance. However, we need to understand that there is a trade-off because the keypoint representations are way more faster and efficient compared to RGB, but this comes at the cost of performance. Now, we show some of the results beyond LRS3 videos on some of the completely unseen real-world videos.
Okay, buddy boy, here it is. You hide my clothes, I'm wearing everything you... Okay, buddy boy, here it is. You hide my clothes, I'm wearing everything you own.
This is another example.
Can I say something? I'm the type of person, if you ask me a question and I don't know the answer, Can I say something? I'm the type of person, if you ask me a question and I don't know the answer, I'm gonna tell you that I don't know.
Okay, so these were the results for task 1 on synchronization. Let us now move on to the second task of identifying who is speaking in a crowd. Here, we'll be showing the original video on the top row for reference, and the predicted speaker will be depicted in green at the bottom.
Work on your body language a bit. You know, when you're all hunched like that, you're shutting the audience out, but when you're relaxed and open, you're inviting them in.
So here, there are a few instances when the camera angle changes and the speaker's face is no longer visible. The traditional lip-sync based methods to determine the active speaker will fail in these instances. But since our model does not use faces, it can successfully predict the active speaker. Here's another result.
No, I'm sick of this, okay? I've had it up to here with you two. Neither of you can come to the party.
So the next results are from the videos that we showed at the beginning of the presentation.
It's the beginning of December. So yeah, very clever machine. This is one of our head shells.
Right.
So
No. Huge ass. He's like the poor man's version of Ryan Reynolds. And like the rich man's version of my most recent.
So in this case, the face and lips are completely hidden, and even in this scenario, our model works well. So to summarize, we have introduced a new task in this work, the task of gesture synchronization, which was never explored before in literature. We devised an architecture and appropriate loss functions to train a model for this task, and also provided a detailed analysis on different types of video representations. Finally, we demonstrated that we can use the pre-trained synchronization network to predict the active speaker in a crowd using gestures alone without the need for the talking head to be visible. There are several interesting future directions, like we saw that there's a gap in performance between keypoints and RGB representations. Thus, finding ways to bridge this gap would be the next step. Exploring the correlation between gestures and language will also be an interesting future direction. All our codes and pre-trained models have been released. Please check our webpage. Thank you for watching.